Okay, today we're going to look at the FAC-1 and show the calibration procedure for it. This is a DC Johnson FAC-1 manufactured in 1984, and it has been refurbished and tested for a customer to use in a restoration of an old European car. The FAC-1 controlled the air-fuel mixture by controlling a bypass frequency valve which bypassed the fuel pressure at the fuel distributor. Here's a brief rundown on the theory of operation for the FAC-1. It has four integrated circuits. The first integrated circuit is a comparator. The second integrated circuit is a voltage controlled oscillator. Third integrated circuit is another comparator. And this fourth integrated circuit here is a 4-channel analog switch. Basically how it works is the oxygen sensor signal comes in over here, passes through this comparator which has a offset voltage set with fixed resistors. The output signal of this comparator is fed into the second comparator as the offset voltage, while the other input for that comparator is fed by this voltage controlled oscillator, and the duty cycle can be adjusted with this potentiometer here. The frequency of the voltage control oscillator is set with this potentiometer here. When the vehicle is cold, this analog switch here does not let the oxygen sensor signal through and instead replaces it with a fixed voltage which is set by this potentiometer here to give it a fixed duty cycle during the cold starting period. Once the signal is output from this comparator, it gets boosted through this power transistor and onto the frequency valve, which we have an example of here, and this power resistor which is in series with the frequency valve in order to control the current level at the frequency valve. One last device here is the voltage regulator, and the voltage regulator on these devices is set between 8 and 10 volts, typically 8.5 volts. This ensures that it continues to function with a low battery situation. So let's plug it in and see how it works. This particular FAC-1 is a used example, and it has been refurbished to as new condition for a customer on customer request. I'm going to connect channel 2 to the oscilloscope right here. This gives me an indication of the frequency before it passes through the power transistor and gets distorted by the coil of the frequency valve. So here we power it up, and you can hear the thing buzzing. This device has already been calibrated, and we can see the green trace is the output frequency before it goes to the power stage. The pink trace is the power stage output, which is inverted from the low power frequency. And this purple trace is a simulated oxygen sensor signal, which is currently set at approximately 440 millivolts. By adjusting the oxygen sensor signal, as you can see, the unit responds by adjusting the duty cycle of the output. A lean condition enriches the output, and a rich condition causes the device to go to the lean side. Now I'm going to ground the switch input for the full throttle switch. This will have the same effect as during a cold start period. And as you can see, it goes to a fixed duty cycle. When it's in cold start or full throttle, the oxygen sensor signal cannot cause the duty cycle of the output to change. Now you can see it's no longer in the full throttle open loop mode, and it's once again being controlled by the oxygen sensor signal. Here's an oxygen sensor signal of 0 volts, and here's an oxygen sensor signal of approximately 1 volt. These rapid excursions of the oxygen sensor signal more closely represent the actual behavior of a real oxygen sensor. Now we're going to simulate a cold starting situation. Under the cold starting situation, the cold start switch will be grounded, which will prevent the device from switching into closed loop. The oxygen sensor signal is 0 because the oxygen sensor is cold. So we'll start the device and it will operate at the fixed duty cycle of 40%, which is what it should be set for in order to warm up in a rich condition. At some point in time, the oxygen sensor begins to warm up and starts functioning, and it will indicate a rich condition. But of course we still have an open loop situation because the vehicle's engine is still cold. Once that cold starting switch opens up, after a brief delay, the unit will switch into closed loop, at which time the oxygen sensor signal controls the duty cycle. One additional setting that we must make is the default duty cycle, which should be 50%. We set this by disconnecting the oxygen sensor. When the oxygen sensor is disconnected, the input signal should float right at 50%, which it is. Now I've reconnected the oxygen sensor, and we have closed loop operation again. Now I'm going to simulate the condition when we go to full throttle and the full throttle vacuum switch closes. It grounds the signal and it operates in open loop at the 40% duty cycle, just as if it were cold. Once again, there will be a brief delay after the switch opens up again before it switches back to closed loop. And that's the theory of operation of the DC Johnson FAC-1. Here's the calibration procedure for the FAC-1. First, adjust the frequency. Frequency should be set so that a full waveform is 14 milliseconds. In this digital oscilloscope screen capture, the period is set for 14 milliseconds and the duty cycle is at 50%. Next we want to set the duty cycle when it is in closed loop but with no input. And that duty cycle should be 50%. We set that with this potentiometer here. The final setting is the cold starting duty cycle or open loop duty cycle, which is used during cold starting and during full throttle events. That duty cycle should be set for 40%, and we set that at this potentiometer here. There you have it. a fully calibrated FAC1. There it is operating in open loop, cold or full throttle condition. Handles the heat just fine. This is a static screen capture from the digital oscilloscope showing an output waveform with a period of 14 milliseconds. This also corresponds to approximately 71 hertz or 71 cycles. As you can see in the text representation below, the duty cycle for this channel, channel 4 on the oscilloscope, is wildly inaccurate. This is because the duty cycle is based upon the peak voltage. So if you are using a digital oscilloscope, you must trust the scale graph and not the text representation when setting the duty cycle. It is also possible to use the undistorted waveform upstream of the output transistor, if preferred. As you can see here, channel 2 is the upstream waveform before it is amplified and sent to the pulse valve. Channel 2 is reporting a 50.1% duty cycle, and this is quite accurate. If you choose to use this waveform for adjustment, keep in mind that it is inverted in relation to the output waveform. A 40% duty cycle at the output waveform will correspond with a 60% duty cycle on this waveform. dcjohnson.com. If you found this video useful, please consider making a small donation to help keep these resources available.